Hello, this is Jiacheng Han, and I'm very happy to come back to present our recent work. I'm currently a PhD student at the University of Wollongong. This is a joint paper with my co-authors, and their names are listed below. As you may know, there are many ADAS features, including adaptive cruise control, autonomous emergency braking, etc., etc. In this paper, we choose one of them to study, that is the lane keeping assist system, or LKAS. Basically, when drivers are distracted or careless when driving, they may not notice their cars are going outside the intended lanes, which is called a lane departure. LKAS can apply assist torque to the steering wheel and keep the car within the lane when it detects such lane departures to make driving safer. And of course, ADAS are safety critical systems, so smart testing strategies are demanded to evaluate and hopefully increase the reliability and robustness of ADAS. To verify the LKAS, there could be multiple ways, like X in the loop, road test, and so on. We choose the Simulink platform of MATLAB to conduct simulation testing, as we consider this is the most convenient way to develop our test approach. And the system and the test is called LKAS with lane detection, which is an example LKAS by the MATLAB team. I will use this short video to show how the LKAS works on the Simulink platform. First, it simulates a careless driving trajectory without LKAS, and you can see that the lane departures happen at the curves. And then it shows that when enabling the LKAS, there's no lane departure, and you may observe some shakings or vibrations at those curves, which means the LKAS is correcting the steering wheel. The figure on the right is a plot of the two simulation results, which shows that the careless driving trajectory in blue are corrected by the LKAS in red. We follow the European New Car Assessment Program, that is the Euro NCAP, in our experiments. It is a popular automotive safety rating system, and it has a test standard specifically for automated driving features such as AEB, LKA, and ELK, etc. And MATLAB has prebuilt scenarios of these three ADAS features so that we can directly use them to test the LKAS on the Simulink platform. In our experiments, we adopt 40 LKA-related scenarios, including 10 categories. These 10 categories have different lane markings and lane departure directions. For example, in the first figure, the lane markings are dashed on the left and solid on the right, and the lane departure is to the left, and the second one has different lane markings and lane departure direction. So basically, these scenario categories are designed to test the LKAS in different conditions, and since there are 4 lateral speeds of the ego car for each category, there are totally 40 LKA scenarios. All of them are adopted as our source test cases. Our Metamorphic relation states that given a driving scenario S, if the LKAS can prevent the ego vehicle from driving outside a lane during simulation, then it should be able to achieve the same after rotating S. This MR1 is a concrete instance of the symmetry Metamorphic relation pattern. We consider that the rotation shouldn't affect the simulation test result of LKAS because the relative pose and trajectory of the ego car with respect to the static scenes are not changed. So according to the MR1, we develop a tool to automatically apply 1 to 359-degree rotations to the 40 source test cases. For example, a source scenario is shown in the left figure, and after a 23-degree rotation, it becomes the right one, without changing the relative pose and trajectory of the ego car with respect to the static scene. So totally, there will be 40 times 359 follow-up test cases. And we have uploaded our test suites to Zenodo at this link below. We also provide a brief tutorial to show how to use them. If you are interested, you can download them, follow the tutorial, and repeat our experiments. And we find that by simulating the 40 pre-built LKAS scenarios, that is, the source execution did not show any lane departures. Like this figure on the left, the predefined lane departures in blue at the design level were corrected by the LKAS in red during simulation. But when we simulate the follow-up scenarios, the violations of MR1 were immediately reviewed. The table on the right provides a summary of the detected failures for all 10 scenario categories with all 4 lateral speeds. The LKAS couldn't prevent the Eagle car from lane departures with the so-called minimum rotation degrees that violated MR1, shown in the last column of the table. Here is a screen record of our experiments. First, it shows a failure that is a lane departure of the Eagle car with 23-degree rotation to the south scenario. Then, it shows the simulation with 22-degree rotation, which successfully keeps the Eagle car within the lane. So when we slightly change the scenarios by rotating only 1 degree, from 22 to 23, the simulation results are totally different. 23-degree one caused an incident, while the 22-degree one didn't. And we find that at the very beginning of the simulation, the Eagle car always has wrong initial orientation, which results in the lane departures later, like this video. We report our findings to the MATLAB team and got their confirm. After the investigation of the failures, they further commented that there could be a mismatch between the input driving scenario file and the internal values being set by the LKAS model. In other words, some values in the input driving scenario file were not properly loaded. That is the initial orientation of the Eagle car. We consider that this case study shows the simplicity and effectiveness of MT. By applying the rotation MR1, we successfully generated corner cases to inspect the system and the test from a different perspective, which seems not covered by the MATLAB team. However, our study has 2 limitations. One is that the reviewed bug is not critical, as the root cause is only related to file handling. Also, in real world, the orientation of the Eagle car doesn't need to be read from external scenario files. Another is that we only investigate one ADAS feature, which is a threat to external validity, for the generalization of our conclusion. And in future, we will explore more ADAS features and combine MT with more ADAS and AD test standards. So that's all for our presentation. Thank you.
In addition to confirming the bug, did you get any feedback from the MATLAB team? Did they find the approach helpful? So that's from Sergio.
Okay, thank you, Pak. Of course, yes. When we reported our bug finding to the MATLAB team, they confirmed the bug first, and then they further investigate. For example, so I also mentioned, I also have some quotations in my presentation that they find that the root cause of this bug is related to the file handling, related to reading the scenario file. Also, they provide a temporary solution to fix this bug. So instead of directly change everything in the GUI, because they provide a GUI graphical user interface. But if we just change everything in the GUI, it won't help to fix this bug, but we need to change the source code. So when we change both the source code and the GUI, we will successfully load the driving scenario file. Otherwise, the bug will be the failure will still be reproduced. But in terms of the whether this approach helpful, they didn't explicitly mention about it, but I hope so.
So I want to follow up this question. Did you actually get the revised version of the software after they said that they have fixed the bug? And have you got another chance to test, the revised version again using the same ML?
No, they don't have a revised version. When you say revised version, does it mean a new version of the LKAS software?
Yeah. The software after fixing the bug.
No, they didn't provide a fixed version. But they gave us a temporary solution to fix the bug manually. As I said, we changed 2 places, and then the bug will disappear. Otherwise, the bug will still maintain.
Okay.
So actually, the MATLAB launches the new version of MATLAB platform twice every year. So they won't fix one bug, particularly for us and for this particular bug. Yeah.
Okay, now I got another question from Professor Alistair Donaldson. So his question is actually mine. I also have a similar question as him. So the question is, do you have idea for other kind of ML that could be useful here beyond rotational symmetry? Because in your paper, you basically just use one ML, right?
Yep. Of course, we during the experiments we have tried a lot of MRs, not a lot of, but some MRs. But most of them are related to geometric transformation. For example, we changed the width of the road, and we do some affine transformation of the map, but only this rotation MR will reveal the bug immediately. So because the root cause is the same, we didn't include the other MRs and the other experiments in our paper. But in terms of the extended work, we have done some new interesting experiments on the verification and validation of the ADAS simulation platform, not related, not just limited to ADAS software, but we want to test the ADAS simulation platform. Also, in this paper, our detected bug is also not the core algorithm of lane keeping list, but it is related to the simulation platform itself. So this simulation, if the LKAS is embedded in a real car, our bug will not be reproduced. It may only happen on the Simulink platform when it involves the file handling. So there are some new MRs that we have included in our extended work, but not in this paper currently. Yeah.
I got another question, but I don't know whether you are able to answer or not. I'm aware that George is a co-author of this paper, right?
Yeah.
And I know that George also published another paper also related to autonomous driving in CACM, Communication of the ACM in 2016. And I would like to know what is the relationship between these two papers and what are the differences between these two papers?
Okay. So yes, I I have read the CSM paper for many times. It inspires me quite a lot. And in terms of the similarity and difference, so first the similarity of these two between these two papers, the MR is. So first we look at the difference. The MR is quite different. So for the CSM paper, they they combine fuzzing and MT to inject some to generate some random points to the point cloud data in terms of the LiDAR perception module. But in our paper, we directly apply the rotation to the perception of the ego car, which means when I say perception, it means the map. So everything can be perceived by the ego car is its surroundings. So we rotate everything with respect to the map, but we didn't change the relative pose of the scenes with respect to the ego car. So our methods are different, but our similarity is similar. We both, how to say, we both verify and report genuine bugs of real-world software, and this is our interest. We are very eager to find genuine new bugs of the very popular software. Let me see.
Now I got another question from Alistair. Maybe I think you have maybe 2 minutes more to answer his question. So his question is: did you consider using code coverage as another metric to see whether your follow-up tests are increasing test follow-ups?
Increasing test thoroughness. We can. So from my own perspective, the machine learning applications it's better not to use code coverage for the verification. For me, I will not choose the code coverage as a testing criteria for the verification of machine learning application. But of course we can, because our rotated scenarios will cover some new logic in the code level. Otherwise, there's no bug detected. So just because our follow-up rotated scenarios can cover some new parts of the whole program, then we can detect some bugs. Of course, the code coverage will be different, but the different code coverage will not imply the bug, the existence of the bug, especially from my own perspective, especially for the machine learning applications. Okay. Thank you.
Thank you. I think